Okay, so we have Lucas Janson today from Harvard Department of Statistics. Welcome, Lucas, and talk about your work, please.
Yeah, thanks so much for having me. I think you said it's already the culture here, but definitely don't be shy about interrupting me. The point of this is to share the work with you guys and hear what you think. This is it's sort of a statistical work that I think has a really nice application to astronomical point source detection, and I've sort of targeted this talk towards the astrophysics community. But my hope is that I can learn from you guys about how we might do things differently if we wanted to make this even more useful for your community, and how, if there are other sort of interesting offshoots from it, I would love to hear that. So yeah, I'll just get started. Also, I have, so here's my most important slide. This is introducing my co-author, Asher, who is he was an undergraduate working with me, and now he's a first-year PhD student. We started this while he was an undergraduate here, and he's at Stanford now. He's on the call, so maybe if people have questions just for clarification or something, and they don't want to, interrupt the flow of the talk, which by the way, please do interrupt me. If you type them into the chat, Asher can probably answer them pretty quickly too. But yeah, good to have him here, and look out for him, because he's going to continue to do really great work throughout his PhD, and then all of you here should try and hire him. All right, here's an outline of the talk. I'm going to briefly talk about motivation, then formally state the problem and talk about the method BLiP, briefly talk about simulations, and then, actually, these last two bullet points are in the wrong order because I flipped the order so that I would focus more on the point source detection application for you all. But I'm going to spend most of the time on that, and then I probably briefly maybe we'll talk about the fine mapping application. Okay, so here's my cartoon plot of astronomical point source detection. The red X's are true locations of point sources in a little grid of cells. This is a pixelated image. You can see the pixels. It's like 10 by 10 pixels or something. And the darkness of the color is the intensity of the light coming from hitting the image. And so of course, it's a little darker near the X's. It's not immediately obvious just looking at the data without the red X's, which is of course not part of the data, exactly where those X's lie. And I think a natural goal here would be to try and find as many of the X's as possible, and for each of those X's, identify as tightly as possible exactly where they're located. And I think it should be clear, hopefully to everyone here, but also from looking at this picture, that it's not mathematically possible to identify the locations of those X's exactly from this data, right? The pixels, the point spread function are all going to make that a little bit challenging. And so, we sort of want to do the best we can and also find as many signals as possible. So I think I don't even have a slide on it, but the same problem arises in genetic fine mapping, but sort of a one-dimensional version of this. This is sort of 2 dimensions. We want to find a bunch of regions which identify the red X's. The same thing happens in genetic fine mapping, where you want to find regions of the genome that contain causal mutations. It happens in change point detection and time series, where you want to identify regions of time that with high probability contain a change point. And in all of those cases, you sort of can't identify where the signal is exactly, but there are multiple signals. So you want to both identify as many signals as possible. And for each signal, you want to identify it as narrowly or at as high resolution as possible. And so that's sort of our generic problem statement, which I'll formalize in a minute. But first, I want to talk about sort of a naive approach one could take to doing this, and why it's not the best approach, and why we want to do something different. So if L is our space of potential signal location, so this is the night sky in an astronomical survey, then one thing we could do is we could pre-specify a partition of L into a whole bunch of disjoint regions, and then we could do some sort of selection. So we could do that via a Bayesian method, we could do it via a frequentist method, whatever you wanted, but we could basically select regions. And this would allow our outputted regions to be disjoint, which is nice. It helps with interpretability if each of our regions doesn't overlap with each other. It also helps us avoid sort of double counting both false positives and true positives. And there are a bunch of methods for controlling false discoveries that we could employ here. because we sort of have a fixed set of potential regions that we're going to discover. The problem is it's not really clear how to pre-specify that partition in advance. We need to, truly partition the data. If we think about the night sky, there are going to be boundaries between these regions. And what if there's a star that falls right on the boundary, right? Then probably we're not going to do a very good job of capturing it. And I think this is really the problem here. And what makes this problem kind of interesting is that what we want to do is do adaptive region detection. And the reason is that it's really kind of impossible to pre-specify a partition in an optimal way without basically knowing too much about the problem in advance. And this is sort of a brief toy example. The same type of problem that I mentioned in genetic fine mapping can be sort of made easier to think about in a simple variable selection problem where you have highly correlated variables. And so your sort of regions correspond to a set of variables that you discover, and you want to find the variables that have a true coefficient in the model with y. And so here, if we think about a regression problem where there's just two variables and they're very highly correlated, and only x1 is a true variable, it's the only one that has a true coefficient in the model for y, then basically the question of partitioning is, do we partition x into x1 and x2, or do we combine x1 and x2 into just a single group or region? And this shows the power of those two approaches. And we can see that for very small signals, we have a fair bit of power to detect the pair x1, x2, but almost no power to detect x1 individually. Again, that makes sense because of the strong correlations. But as the signal size grows, we eventually do get power to detect x1, which means that if our signal size is large, which we wouldn't know a priori, if our signal size is large, we'd really like to partition things into x1 and x2 because detecting x1 alone is far more informative than detecting x1 and x2 jointly. And so basically, these are sort of the two choices of partition here. And depending on where you sit on the x-axis, that's the main takeaway from this plot, you would make a different choice between the red curve or the blue curve. But the problem is you have to choose between the red curve or the blue curve before looking at your data, which is the only way that you would know where you sit on the x-axis. And so this is what motivates our approach to do an adaptive signal detection approach that looks at the data first and uses the data to sort of inform what are good candidate regions, and then tries to control some sort of error rate on selecting those regions. Yes, question from David.
Yeah, so can you just clarify, when you say power to detect x1 or x1, x2, do you mean to detect, or like in the regression problem, that you would say that either x1 or x2 is the regressor?
Exactly, right. So we would detect the region and we would say, our conclusion is that at least one of these is a true discovery, but we don't know which one.
Yeah.
Possibly both. Yeah, exactly. And so that's why it's less informative than if we just detected x1 alone, because we would be telling you exactly where it is. And again, the analog here is if we sort of detected a larger region of space, we'd be saying there's a signal in this region of space, but we don't know exactly where it is. Whereas if we detect a smaller subregion of space, that's a more informative discovery, but it's harder to make.
One more question. So in this approach, when you say signal, it's signal above a background. You have some background, and then you're looking for the signal, right? So a priori, you don't know the strength of the signal above the background level when you.
That's right. Yes. So I mean, in this toy example, the background is sort of just zero, right? That's our baseline. In the point source detection problem, yeah, we assume there's some sort of background, and that we can define some notion of a signal which stands out from the background. That sort of is what I'm assuming someone can define what a signal is, right? We have to be able to define that in order to talk about it. If it's really conflated with the background, that's sort of a separate problem that is a very important problem that we're not trying to help you solve, basically. But someone has to define what a signal is, and be able to, at least in principle, if you sort of had no noise in your data or no optical artifacts, be able to define what are signals and what's background.
Okay, we can go back to this later when you finish, because
Sure.
there is,
Yes.
Yeah, I have follow-up questions.
Great. Okay, so this is motivating our adaptive approach, and let me now formalize the problem statement. So we don't want to. The idea here is we don't want to narrow our potential discovery regions till after seeing the data, and so what we want to do is we want to look at the data first, and then output a set of regions. So G1 through GR, that's an output of our procedure, which means that The G's are a random function of the data if we think of the data as random. R is also a function of the data and hence random if we think of the data as random. And this is what we want to solve. So we want to maximize some notion of power, and I haven't told you quite yet what that power function is, but bear with me for a moment. I want to maximize some notion of power or expected power subject to some sort of control over false discoveries. So here we wrote down the false discovery rate. We could use other notions of error rate. False discovery rate is sort of a canonical choice in statistics. So we use that as a running example, but we'll briefly mention some other error rates we can control as well. And then the last thing that we want to impose, which one could discuss the utility of, is that I think we want our regions to be disjoint. We want to output regions that are disjoint, and I think that really helps with interpretability. It certainly helps with even computing a false discovery rate. If you have overlapping regions, it's not really clear what are false discoveries if one of them contains something but the other one doesn't, or if they overlap and there's a signal in the overlap, do we count both of those as true discoveries? Neither of them as true discoveries? It's sort of unclear. Similarly, it helps to define power if we force all the outputted regions to be disjoint. So that's going to be another constraint in our problem, and this is sort of what we would like to solve if I can define the power function. So what should our power function look like? Well, we think that we should make as many true discoveries as possible. So we want to find as many signals as possible. And then we also want each of the discovered regions to be as small as possible, because that's going to narrow down the location of the signal as much as possible. The problem, of course, is that these two objectives are not perfectly aligned, which means we need to somehow incorporate both of them into a single scalar measure in order for this problem statement to even be well defined. And that's really our first contribution, is to define a resolution adaptive notion of power that incorporates both of these two objectives. And I think is critical for trying to solve this problem, because again, without it, never mind an actual method to solve it, it's not really even clear what we're trying to do. It's not clear how we would compare two methods that are trying to solve this problem. It's not clear how we would really measure success in this problem. And so although there are some existing methods for solving problems like this, as far as we know, no one has really formalized what the objective is in this problem. And I think that's a critical thing to do. All right, so how are we going to do that? We're going to define this blue function, and we're going to do it through a weighting function. So basically, for a discovered region G, I'm going to assign it some weight, which tells me the value of discovering group G. So as we said, we should sort of penalize larger groups, right? So we want the weight to be higher for smaller groups, smaller for larger groups. A very natural choice might be 1 over the size of G. In the astronomical point source detection problem, this gets a little weird because G can sort of be arbitrarily small, and so this could blow up. What we ended up thinking about was actually 1 over the radius, because we only considered G that were circles, since that seemed to, we didn't think at least that there's too much directionality to the night sky. We figured, circles are nice and spherically symmetric by definition. And so we would only consider discovering regions that were circles. And then we could use sort of 1 over the radius as a natural weight on a discovered group. And so, then the weight that you assign that group measures sort of, I think very naturally, the resolution at which you measure it. What's the distance from the center to any signal that lies in that region? It's going to be bounded by the radius. We can also think about a totally different weighting function that I'll talk about at the end when I apply this, just to show the sort of flexibility of this framework. If we wanted to, instead of discovering each signal as precisely as possible, we instead wanted to be really sure about exactly how many point sources each region G contains that we discover. So, we don't just want to say, oh, there's at least 1 signal in this region. I actually want to say, okay, there's exactly 1, or there's exactly 3 signals in this region. I can't narrow it down further, but I want to be able to tell you exactly how many point sources are in that region. We can handle that too. So the way to think about that is we would pair each G, each discovered region, with a J, which is a region, but now a subregion of the non-negative integers, which represents the possible number of sources in G. So for instance, J could be like, 2, 3, 4, right? The set 2, 3, 4, which would say that there's either 2, 3, or 4 point sources in G. And if we pair these G and J together, now we need to assign a weight that's a function of both G and J. And we could assign that weight as 1 over the size of J, which means, again, we want to be as sure as possible about the number of point sources in the region J, right? So this is another very different, we call this a separation-based weight function, and could also sort of capture a different objective. But I think there's a number of different objectives people could try and capture with this framework, and I'd be interested to hear from other people if they think there are other things they'd want to optimize. All right, so now that we have these weights, now I can define my power function. That was that thing in blue from 2 slides ago. I'm going to define this power function as, and this is sort of something we might call it sort of an empirical power, right? Like how much value do I give to a set of discoveries, G1 through GR, and I'm just going to sum over those discoveries, and I'm going to sum the weights over those discoveries, except of course, I'm only going to give myself a non-negative weight if that's a true discovery, right? So I'm only summing over the true discoveries. That's what the IGR stands for. It's just the indicator that GR actually contains a signal, because if it doesn't contain a signal, it doesn't count. We would also, in the separation-based weight function, right, that indicator would be the indicator that it contains the right number of signals, right? It contains a number of signals which is in the set J. So, you know, I guess, again, I tells you it's sort of a true discovery, weight tells you the weight you assign to that discovery, and then we sum over all the projections. All right, and now that we have this power function, we can look at the Bayesian expected power, because after all, this is going to be a Bayesian signal discovery method. So the expected power given the data, that's our Bayesian expected power. We just plug in our equation for the power and then see that this simplifies reasonably well to a sum over all possible regions. So sum over all G that are subsets of L. So that's a big sum. We'll get back to that. But for each of those regions, the sum and is just a product of the weight, the posterior inclusion probability, the P sub G, and XG, which is just the indicator of whether we discover region G or not. And so we can think of XG as actually being our optimization variables, right? That's what our method outputs. It chooses for each region whether it wants to discover it or not. And then the PGs, that's not part of our method. That would come from some, you know, Bayesian posterior approximation. That would be an output of the posterior, as we could compute these PGs from the posterior, and then those would be an input to our method. All right, you're going to see this this equation again in a second, where I sort of write everything together now. This is our sort of full optimal Bayesian, you know, decision theoretic perfect thing we would do if we could solve this problem, which is to maximize the power. I'm just rewriting it here. Again, it's the sum of the product of PG, WG, and XG, such that the false discovery rate is controlled. Again, we can handle other error rates, but for now, let's stick with the false discovery rate. Then my third constraint is that all discoveries are disjoint. This one's a little weird to parse, so I'm summing over all regions G that contain a location little l. So little l is an element of mathcal L, which is the set of all locations. And I'm going to have that constraint there for every single possible location. If you're paying really close attention, you may have noticed that in the Astro application, the mathcal L is actually a continuous set. And so there are infinitely many, uncountably infinitely many, in fact, little L's. And so this is, you know, really intractable because this is infinitely many constraints in an optimization problem. And then that brings us to the fourth problem, the fourth line, which is just the integer constraint that we either discover or we do not discover every region, 0 or 1. Okay. So our first and our third constraints are linear, which is a good thing. Again, as I said, the third line is not so good because there's many of them, although we have a way of dealing with that. The second line is not obviously good because it's not obviously a convex constraint if we wanted to do this as an optimization problem. The fourth line is definitely bad. That's a highly non-convex constraint. It's an integer constraint. We don't like that. And the last thing that's bad is the tiny max over all subsets of mathcal L, because there's way, way, way too many of those. That's a problem we're going to have to deal with. So I have sort of all this red in this optimization problem, and I'm going to try and turn it all blue in the next few slides so that we can tractably solve this problem. Let me pause here to see if everyone's sort of okay with what I'm trying to solve.
I have one question.
Please,
You probably said that. How do you assign the weights to the regions?
It's a user-defined choice. So you have to pick. That's sort of what this slide was all about.
All right. Okay. All right.
It doesn't come from the data, right? That's something that you define. It really depends on what you want out of your data.
Okay.
So we have some sort of default choices, but we would love to hear if people sort of have suggestions for other weights that would be particularly interesting in Astro applications.
Okay.
Great. Okay, so yeah, let's get rid of some of this red. So the first piece of red that's easy to get rid of is the FDR constraint. Well, it turns out this is just a linear constraint in disguise. We just basically need to move the denominator over to the right-hand side and then subtract, and we get a nice linear constraint. There's nothing more to it. Okay, so I've turned the FDR constraint blue. That's nice. It's a nice linear constraint. We always want linearity in optimization problems, linear objective function, linear constraints. Those are all good things to have. So now that we've linearized this, we now have what's called a mixed integer linear program. It's still convex because of the integer constraint, but we have pretty fast solvers for reasonably small problems. Maybe, hundreds to thousands of optimization variables, which we're sort of nowhere close to being on the scale of when we're doing Astro applications. So we're still going to need to make our lives much easier. But it's important that we are able to solve this problem if the number of optimization variables is quite small, even though it's non-convex. Okay, so the next constraint we're going to deal with is that fourth line, and we're just going to convexify it. We're going to take the convex hull of 0, 1. That's it. That's a pretty common thing to do in optimization problems. When you have a non-convex problem, you solve the convex relaxation of the problem, and that's exactly what we're doing here. There's a question of how good our solution is going to be, and we're going to talk about that in a second. But that's sort of the strategy we're going to take. This is now a linear program, and linear programs are a super mature technology. We have really, really fast algorithms that can solve these for a lot of optimization problems and a lot of optimization variables and a lot of constraints. So super efficient, and we're going to try and leverage that. But first, I want to talk about the difference between the linear program and the mixed integer linear program. So I told you that, let's pretend for the moment at least, that we can easily get the exact solution to the linear program, the linear relaxation, and call that xg star. And then we can just look at xg star. If it happens to be all integers, then we're done. We've solved the mixed integer linear program, because linear program is a strict relaxation of the MILP. But usually that won't be the case. And what we're going to do in that case is we're actually going to fix all of the integer solutions. So maybe some of the solutions will be integers. We're going to fix those. We're not going to let those vary anymore. But we're going to look at all the ones that are not integers. And we're going to solve a new mixed integer linear program, right? So we're going to remove the convex relaxation, but only optimize over the set of xg stars, which are not integers. So it's at least a smaller mixed integer linear program than we solved before. And I'm going to call that new solution, which is sort of partially the old solution and then partially the new solution, all of which have to be integers because I've now solved the mixed integer linear program on the non-integer old solutions. I'm going to call that xg star star. And in general, this need not be a solution to the mixed integer linear program, right? It is feasible for the mixed integer linear program because it satisfies all the constraints of the mixed integer linear program, but it's not necessarily optimal. That said, here's what we found. These are two distinct facts that are empirical facts that we don't, I think, fully understand, although we have maybe some guesses as to what's going on. But what happens is that when we get xg star, very few of them are not integers. So even when we have tens of thousands of optimization variables, tens of thousands of different xg's, we still find single-digit numbers of them are not integers, which means that the mixed integer linear program that we solve is actually only of single-digit dimensionality, and these we can do super fast. So from a computational efficiency standpoint, this is really important. Again, we don't really have a proof that this is always going to happen, but it seems to always happen empirically. And of course, if it doesn't, you'll know. So it's not like you'll be tricked or anything. But we've basically found that anytime you run our algorithm, you end up with a tiny number of non-integer solutions. And so the MILP runs super fast, and you can be sure that it's sort of working. The second fact, which is maybe even more important, is that this sort of two-part algorithm, this two-stage algorithm, seems to achieve essentially optimal solutions for the original mixed integer linear program, the non-relaxed one that was too big to solve. And the reason we know that is that we can actually measure exactly an upper bound for the suboptimality of xg star star, because the solution to the linear program is always an upper bound to the solution to the mixed integer linear program, because again, one is a strict relaxation of the other. And so if we look at the difference between the objective function values for xg star and xg star star, this is an upper bound mathematically exactly for the suboptimality gap of xg star star. So if this is small, we know that we're not far off from the true optimum of the original mixed integer linear program that we were trying to solve. And this plot basically just confirms that. Here's, it's a few different simulations over a few different dimensionalities. These all have over 50,000 optimization variables, so different candidate groups that we're considering. And what we see here is basically one line, but in fact, we're plotting two lines. And the two lines are the solution that's obtained by BLiP, and the other line is the upper bound that's obtained by looking at the relaxed linear programs solution. And we see that they're on top of each other. I mean, they're indistinguishable. And we found this uniformly throughout every simulation we tried. And we ran many, many of these in different settings, different simulations and real data. And we always found that the two solutions were almost indistinguishable. Not exactly indistinguishable, right? We're not claiming these are exactly equal, but they're so close to being equal that for all intents and purposes, we've basically solved the mixed integer linear program. So this is nice. There's still, one thing I promised you, which is that we can solve really big linear programs, but not 2 to the L big, not the power set of all locations big. And so I still need to cut that down a little bit. And the way that we did that is to just restrict to a set of regions, which is now the script G, which is some subset of all possible regions in L. And so I haven't really done much other than change the set of optimization variables I'm considering, and I've made it smaller. And this is basically, up to a computational constraint. So however much you can compute, you can take G to be that large. Again, because linear programming is really fast, we can do this for a very large number of script G. So we can still sort of be very, very adaptive in what the set of candidate groups we consider before looking at data. And then after we look at the data, right, we of course narrow that down to the ones we actually discover. But yeah, the point is that this input set can still be very, very large. And we can choose it, I think, in very reasonable ways. So essentially, first of all, we probably only want to consider contiguous regions. In principle, there are regions which are non-contiguous. We could discover, a region that's, a little square here and a little trapezoid down here, and say like, okay, we think there's a star in some part of this disjoint region. But that's not very useful or interpretable. And so probably we only want contiguous regions that are all in one piece. And I think for astronomy, it might be natural to consider even fairly simple shapes like circles. And so what we did when we did the astronomy application is we actually just considered a whole bunch of circles of varying radii and varying centers. And so you can sort of, place a whole lot of circles in the night sky with different centers, different radii, so they're different size circles too. And you can cover, a lot of what you might want to discover doing that with, a large number of circles, but, not more than 10 to the 8 circles, basically. And so we can basically sort of cover all the candidate groups we might want to really realistically discover without actually having to go to 2 to the L number of candidate groups.
Can I just ask a question? Just jump in.
Yeah.
Why circles and not squares? I mean, because I just imagine I imagine an image that you would want to have you want to have disjoint, but also cover the whole thing.
So
Partition,
there's no reason that the candidate groups need to be disjoint. Ultimately, what we're going to reject need to be disjoint, but we don't need the candidates to be disjoint.
Candidates, yeah.
That's important. I mean, we would certainly, even if we were considering squares, we would want to have squares of different sizes that definitely overlapped in the candidate regions.
Yeah.
And
because then you would give yourself the option of saying in this big square there might be something if that's all your data could really tell you.
Exactly. Because the alternative is basically to just discover nothing if you only consider smaller squares.
Yeah.
Exactly. That said, there's no reason you have to only do circles, right? If you can do all the circles, you could also do all the squares of the same radius, and it would only double the size of G, which is, fine. And you can add them all together, right? So we have sort of a couple different strategies here for different types of problems, but you can also combine strategies. I think we actually did this. So what we do is we apply, I'll pause here because it's relevant. When we applied this to an existing Bayesian analysis of a whole bunch of point source data, that original analysis looked at all the MAP estimates of where the stars were. And I believe we took sort of a grid of centers and a grid of radii for the circles that we considered as candidate regions. But then we added to that all the centers that corresponded to the max a posteriori locations spat out by the Bayesian algorithm. So we can sort of even look at the data in determining what set of G we want to use here.
Yeah,
that's totally.
And incidentally, at least to me, maybe one of the astronomers will have something else to say, but it seems to me that the constraint of saying that G is essentially finite there is not really a constraint, because the instruments have finite resolution, right? You're never going to want to have your circles be too small or squares be too small, and you'll have a sense of how small they can be.
I think that's probably right. I mean, one thing we discovered that at least wasn't obvious to us initially is that you can make discoveries at very sub-pixel resolution. So, yeah. There is more information than just at the pixel resolution. So at least it wasn't obvious to us a priori what the sort of smallest resolution you could possibly discover is. It seems like that maybe depends on the signal size, right? If you have a really intense source, you have a huge point spread function, which is actually going to narrow down the center quite precisely. But maybe if you have a bound on the intensity of any of the stars in your image, you would sort of
from the amount of data you actually have, you have some sense of those limits, I guess.
Absolutely.
I mean, maybe 10 to the 8th isn't as big as it sounds when you start thinking about all the possible radii and everything. But
yeah, in a two-dimensional image, I think it's still pretty good. But
sounds pretty big.
As soon as you go to a higher dimension, yeah, it sounds big, right? Good. So the other, I think, important point here is that we can do what we call adaptive pruning, where we sort of initially consider a really, really, really big script G, and then we can look at all the PIPs, but not actually plug most of them into the optimization problem. And the way we do that is we look at the PIPs, and if we see a PIP that's like, so again, this is the probability that it contains a signal. If that probability is like, 10%, and we're trying to control the false discovery rate at 10%, right, then that group is probably basically has a 90% probability of not having a signal in it. And so there's almost no way we would ever discover that region while controlling the false discovery rate. So we can basically just completely discard that group and not even consider it in our optimization. And technically, we could lose a little bit of power from this. In practice, I think it's pretty obvious that we really shouldn't lose much of any power. It would be a little weird if we discovered a region that has such a low probability of containing a signal. I think we might question the utility of the method if it was doing that anyway. So basically, yeah, we can throw out a whole bunch of regions beforehand that the Bayesian inference already tells us are very unlikely to contain a signal. And that's already going to reduce our dimensionality considerably before we plug it into the algorithm. Okay, now when we put these things all together, that's what gives us Bayesian linear programming. That's our method. And again, the input is, in some sense, the hard part is actually doing the Bayesian inference over, for the Astro application, sort of over possible star maps, basically, of where the stars are. And this can be done in a number of different ways. We built on top of, in our application, a variational inference method called StarNet. And there are other ways. In principle, one could do it. Really, any Bayesian posterior approximation algorithm should be compatible with our method, because all you need to be able to do is pull out PIPs relatively efficiently. And basically anything you can get samples from, you can very efficiently draw PIPs from by just computing how many of those samples contain a signal in the region that you care about.
So the PIP, just to be clear, that you went over that part quite quickly a few slides back. The PIP are all summaries of the posterior distribution, and so all of your modeling assumptions, Poisson data and point spread functions, all of that stuff goes into the PIP. Yeah,
exactly. That's right. And there's definitely a question here about if you have imperfect PIPs, which, let's face it, you're always going to have imperfect PIPs. You know, how does that propagate into invalidity potentially in the BLiP output? And we have a whole bunch of appendix sections about that and some heuristics for sort of making sure that your PIPs, if they're not perfect, don't throw you off too much when you run them through BLiP. But I think the strongest case that we're somewhat robust is going to be the real data application, where we show we actually have remarkably good FDR control in the real data. So yeah, just before I get to that, this is just showing that computationally BLiP is really fast relative to what I just called the hard part, which is actually doing the Bayesian inference. So this is a number of different Bayesian inference methods. This is all for variable selection problems because there are sort of more existing methods for doing that. And whether you take an MCMC approach or a variational approach, basically either way, it's so much more expensive to compute the PIPs in the first place to do the Bayesian approximation than it is to do BLiP, that BLiP is essentially a negligible additional cost on top of that. So that's sort of nice. In some sense, you get BLiP for free if you've already been able to do the Bayesian posterior approximation. Another way maybe to think about this is that we sort of reduced the problem of this adaptive signal discovery into one that's sort of purely and a very well studied problem of approximating the posterior of a distribution. All right, so now we're going to compare with some alternatives. This is going to look very variable selection centric because we were able to find a lot more alternatives for variable selection than for point source detection, which is not really a regression problem. So this is really a regression problem. So maybe I'll go sort of quickly, but there are some methods. The Bayesian methods come from the genetic fine mapping literature. The frequentist methods are just sort of multiple testing methods that could be used, although they have fairly strong assumptions about the p-value distributions that really don't hold in practice. But we'll see how that propagates into still controlling the false discovery rate. And then, as we said, we can put BLiP on top of any Bayesian method. And so here we also implemented our own just spike and slab Gibbs sampler, nothing fancy, and combined it with BLiP to see what we do. So here's a whole lot of curves. Since this isn't a fine mapping community, you probably don't care about the details of the fine mapping methods too much. The main takeaways are that when you combine, can people see my cursor?
Yes.
Yes, okay. When you combine BLiP with the linear spike and slab sampler, that's basically the best thing you can do. And we have two curves here. One is the dark blue curve. That's the highest power one everywhere. That's sort of using a well-specified prior for doing the posterior samples. That said, this is a pretty high dimensional problem. We don't really believe that the MCMC sampling has actually converged here, but it doesn't seem to cause us any problem because we control the false discovery rate of that dark blue curve always. The light blue curve is the same thing, except now we use a somewhat misspecified prior, and we still don't see a big problem. The power is very similar, and the false discovery rate is still basically controlled everywhere. SUSY is a variational approximation that we can combine with BLiP. We can see that variational approximation is much better in very sparse settings. The dark red line has high power when the sparsity, which is S at the top of each panel, is 1 in 100. It's much less powerful when the sparsity is about 20%. And even though point source detection is not a variable selection problem, I think sparsity is actually kind of a universal thing. We would expect most of the image to not contain a star. And so I think we would think of point source detection as a fairly sparse signal discovery problem still. And then we see also that this variational approximation SUSY, it does violate false discovery rate control due to the variational approximation. But when combined with BLiP, the violation is no worse, and actually sort of surprisingly, we don't have an explanation for that really. Well, okay, we have some explanation for it, but it's very specific to the SUSY variational approximation. It's actually slightly better in terms of false discovery rate control. So it doesn't seem like errors in the PIPs, at least in the cases we've tried, cause huge problems for when you plug those PIPs into BLiP to do the adaptive signal discovery. Okay, so here's the, the simulation tells us, hopefully we're not doing something crazy. It seems to work. This is just a quick note that we can handle other error rates, right? The sort of main result in some sense is that if we write down the optimization problem we want to solve, that we can sort of figure out this heuristic way of finding a really good solution. And it seems to work sort of surprisingly well, and that it's both efficient and finds a solution that's essentially optimal. And it turns out that the same thing is true, even if we change the false discovery rate to the local false discovery rate or the per family error rate, which is basically something we could use to control the family-wise error rate. So any of these sort of standard type 1 error metrics that you could use, the same phenomenon occurs. So there's each of these colors has two curves, a solid curve and a dashed curve, and they lie right on top of each other, which tells us that we're finding basically the optimal solution with a very efficient algorithm, despite the original optimization being convex and very high dimensional. This is a quick picture just for the time series change point detection problem, but I think I'm going to skip this and instead get to the application. Okay, so this is what we applied our method to in Astro. So it's a 100 by 100 pixel sub-image of the Messier 2 star cluster from the Sloan Digital Sky Survey. And this was nice because we have essentially a ground truth from the much more powerful Hubble Space Telescope, which was pointed at the same region of sky at some point. And so we basically know where all the stars are. And so we can actually evaluate the false discovery rate of BLiP to see if it's doing what we want it to, as well as the true discovery rate of BLiP and any other methods. We built on top of this very recent Bayesian analysis of the same data called StarNet. It's an approximation. That's a variational approximation. They basically just output the MAPs. They don't actually output regions officially, but they give themselves sort of half a pixel of slack to say, like, we call this a true discovery if the MAP we output is within half a pixel of a real star. And so we sort of interpret that slightly liberally as, well, they're basically outputting the MAPs plus or minus a half a pixel in the 2 dimensions. And so we can think of them as basically outputting boxes. And that's what we're going to compare to. Here is a continuous space of locations, L, which I didn't really tell you how we addressed, but Asher came up with a clever way to turn that into a finite thing. Basically, you use the fact that there's only finitely many G, even though there's infinitely many L. And so you actually don't need infinitely many constraints to represent the disjointness constraint. You can do it with finite many of them. And we ran this for 15 different nominal FDR levels, and it took 10 minutes total to run all 15 of them. So less than a minute for each FDR level. And here's just a picture to give you a sense of what the output looks like. So all the way on the right is what we call the StarNet output, which is MAPs plus or minus half a pixel, and they consider the pixels in XY space, so it really is little squares. And then what we output are circles, and these are 3 different nominal false discovery rates: 5%, 10%, and 25%. And you can sort of see, especially if you zoom in on the little dashed subregion, you can see that when we control it fairly stringently at 5%, we find some larger regions that do a decent job of capturing stars, but not very narrowly. And that as we, increase the nominal false discovery rate, so we allow ourselves to be a little more liberal with our discoveries, we start to be able to make discoveries at higher resolution. And we're able to do all of this while maintaining control over the false discovery. So red circles here are false discoveries, blue circles are true discoveries. And it may not be obvious from looking at this image that we're doing better than StarMap. I'll show you the next slide will make that more clear. But I want to emphasize that actually the most important discoveries in terms of our objective function are the smallest discoveries. So you can see there's like this tiny blue dot. Well, you almost miss it from looking at the image because it's right next to a green dot. But actually that's really important, right? That's a really useful discovery. We basically discovered that star to a really tiny resolution. Remember that the squares on the right-hand plot are basically 1 pixel by 1 pixel, right? So this is super sub-pixel resolution discovery that we're able to make here. And there are a number of them here, here, here that we're able to make. And so we're actually making quite a few discoveries with relatively few false discoveries compared to StarNet.
Can I interrupt again?
Please.
There's this Bayesian analysis that leads to your PIPs, right? And that's StarNet in this case, right? If I'm understanding correctly. So does that, I mean, so it seems like it has to be that underlying model has to give you estimates of the locations of the sources, and as opposed, and so this number of sources is a variable in that underlying model as well.
Yes, there's a prior on it, so it's not assumed known ahead of time.
Yeah, so that it somehow, I guess this is your map estimate or their map estimate, and that the map estimate, it's a map estimate of the locations of the sources, but presumably also of the number of sources.
I guess there is both, although I think what they call map estimates are just any local optimum in the sort of entire posterior landscape.
I see. So maybe it's kind of not a non-parametric model of the intensity, and that where there's a mode in that
Exactly.
That's what you call a source. I see.
Which need not correspond to the MAP for the number of stars, right? Because they could have a mode that's actually very low. And indeed, that's actually a key difference between ours. We'll see in the next slide that we are able to control false discoveries much better than they are. And we think that's in part because there are local modes that actually don't correspond to very high modes or large mass modes. And so we're able to sort of filter those out because we see like, oh, actually, there's not that much mass here. It's not likely to be a true discovery, even though it's sort of locally a good region in some sense.
Right. If they have a flexible model, any fluctuation in the background will show up as a mode.
Yeah, it didn't seem to be quite that bad. So maybe there's enough.
It's not so flexible.
Yeah. I don't want to beat on their analysis too much. I think they did a reasonable job, and their posterior approximation was fantastic, and that's what we built on. So we're very happy with that part. But I think sort of what they drew out of it could be improved, and that's sort of what BLiP does. Okay, so let's see exactly how BLiP does that, how much BLiP does that. So the first plot, and maybe the one I find most surprising, is the left-hand plot, which is just the realized false discovery proportion versus the nominal false discovery rate that we are trying to control at. And I think this is a remarkably good agreement for a real data set. It's not perfect. The blue line is a little above the sort of perfect y equals x axis, which is the dashed red line. But it's clear that we're basically doing the right thing. That BLiP is controlling false discoveries, if not perfectly, then extremely well, while also optimizing its objective function. And then the right-hand plot shows the resolution adjusted power. And here we see, our curve, the StarNet plus BLiP curve. So this is power versus false discovery rate. And so, we map out a curve by changing Q. And we already saw that basically RQ basically corresponds to the realized false discovery rate, the x-axis. The way that we map out a curve for StarNet is we sort of change that half pixel radius that they add. We vary that. So we can make that bigger or smaller, and that's going to sort of map out a curve of resolution adjusted power and false discovery rate. And we can see that our curve lies everywhere strictly above their curve, which means we're always doing a better job of trading off power, right? We're sort of Pareto uniformly better than the green curve. I'll just, point out that, at a reasonable false discovery rate of like 10%, we have a realized false discovery rate also of 10% and a resolution adjusted power that's twice as high as that of StarNet's. And so I think it's a pretty big improvement. And as we move to the right, we also see that StarNet actually never achieves a resolution adjusted power higher than about 1500 or so, whereas we are able to go above 2000 if we allow a higher realized FDR. Also, I'll point out that StarNet does not come with any notion of false discovery rate. So if you ran StarNet, you would have no idea where you are on that x-axis, whereas BLiP, again, via the left plot, tells you exactly where you are on that x-axis, basically.
But somehow StarNet does have a knob you can turn to adjust the FDR.
Yeah, except you don't know what the value of the
where
FDR
you are on the What do you know what that knob is? Like what are you adjusting?
We chose that knob. That was our knob. There are other knobs you could turn in principle, I think, but it's basically this slack variable. So instead of half a pixel, we varied that to 1 pixel, 2 pixels. Right, and so it's sort of analogous, right, in that we're making each of these regions bigger or smaller, but in a sort of non-adaptive way, which is what distinguishes this method from our method. And in the same way that they output a non-adaptive set of regions, they have the same slack used for every single discovery. So it seemed at least in keeping with the spirit of what they were doing, even though they didn't report any of these other green tuples. All right, and then last I want to talk about this other weight function that I introduced at the beginning of the talk. If you use this separation-based weight function, you're getting a very different answer. We're no longer penalizing the size of discovered regions at all. We're only penalizing the size of the confidence set for the number of sources in a discovered region. So we want to be confident about how many sources lie in a discovered region. And that's really the only thing we're optimizing for. Again, we see that the realized false discovery proportion is right on target, even slightly better than in the top set of plots. And on the right, we again see that we're beating StarNet by a lot here. I can't actually remember what did we do with StarNet. StarNet outputted what did StarNet output actually for J, Asher?
Oh, it's just one. We picked one because it doesn't do anything.
Yeah, they just made one discovery. So yeah, that and there's a reason that the green points all lie on a line. It's basically there's a sort of linear equation that it has to satisfy. But some things to notice are that the green curve actually never goes below about 30% realized false discovery rate. So if you're using StarNet, you can never get the false discovery rate in this problem below about 30%, whereas the blue curve can go quite low. So it's another thing to note that green curve actually traces out a parabola. If you sort of vary epsilon, it sort of goes out and then back. It's not like, oh, if we just made epsilon smaller, we keep going to the left. That's actually a hard limit that you can't go past. And then we are also able to achieve higher power than anywhere on the green curve for realized FDRs, around 30 to 50%. Yeah, so I'll maybe briefly mention this just because it makes another point that I think is important, which is that in these plots, the y-axis of resolution adjusted power, that's a y-axis that we kind of made up in this talk, right? So you might be worried like, well, okay, come on, you're measuring this against your own yardstick. That's a little unfair. So we're doing the same thing here in fine mapping. Again, we're taking an existing variational approximation to the posterior, and then we're adding BLiP on top of it, and it's giving us an additional power boost. What I want to show you here is that power boost is not just because we defined the power in a different way. This is actually looking at the cumulative frequency of discovered regions and showing that SUSY plus BLiP uniformly dominates SUSY, and that for every size group, it discovers more of that group size than SUSY without BLiP. And so, by any reasonable measure of utility here, that as long as you basically agree with the two sort of axioms that discovering more regions is better and discovering smaller regions is better, then the blue curve has to lie on top of the green curve because it's sort of strictly dominating it. All right, and that's about it. So it's a new method for this problem we call resolution adaptive signal discovery, which we think is relevant to astro folks like yourselves. And we get nice error control. We can verify that we're basically nearly optimally solving the problem, and we get substantial power gains very quickly. Asher wrote some great packages in both Python and R that are super fast to implement this stuff, and hopefully easy to use. If you want to use it and you have trouble, or even if not, definitely let us know. And yeah, we think there's potential for other stuff, and we'd love to hear people's thoughts. Thank you.
Thank you. A very interesting new method. So, any questions? We have people. I don't see any hands. I mean, you can just unmute yourself and ask questions if you want. Yeah. I have my questions from the beginning, which relates to the background and to Poisson data, where our background is pretty sparse in Chandra. Let's say Chandra observations, where we have background is Poisson, so you may have in an image, let's say 100 counts, of a background, which is image 1024 by 1024, right? So the background is very sparse, and the sources could be very faint. So some of false sources may be, having 2 of the background counts together or 3 of the background counts together in a region. So your method, I was wondering if your method can be applied to such a case where, we very, for the sparse data and the, very faint source.
I think the answer is yes. You would just need to incorporate that into your Bayesian model. And I think that, of course, in the sort of limit as I guess the important thing is that there is some background and that the signal is very faint. And of course, if the signal is too faint relative to the background, I mean, you shouldn't, and no method should have very much ability to solve that problem, right? And so what that's going to show up.
Yes, and it is, right? But there is also this argument about density of counts. With, close to your source, you will have more counts. Far away from the source, it will become sparsely located at the background.
Yeah. Well, oh, right. So when I say the like faint signal, I assume that meant like relative to potentially, dense little background blips that came up at the same time. But I guess if, as long as the background is relatively sparse, it should be fairly rare that background, points show up too much together. And so, yeah, you should be able to discover it. Again, as long as it's in the Bayesian model, it should be fine, and it should basically be accounted for in the PIPs, right? So if you see, a couple photons together, your PIP may be relatively high, but as long as you've properly accounted for the background and the potential for the signal, it should properly balance that, and BLiP should work on top of it. And in principle, BLiP should work just fine with, Poisson models and stuff. You don't need.
Yeah, I think we can, it is a way to test it, because, you have a long observation, you can have a chunk of the observation, which is very, small. In the long one, you may have, more signal in your source.
Yes.
It would be interesting to see, when is the breaking point of the applications.
And are there data sets like that basically stare at one region of sky for a long time?
Yeah, so typically X-ray observations take a long time, right? So our deep observations can have 1 megasecond, so go through a few days of staring at one point of the sky, and then the background rate, of course, becomes higher. But your sources, especially bigger, stronger sources are more visible. And if you have even 100 kilosecond observations, you can divide in 10 different ones and 10 kilosecond chunks, and you can see if there is consistency kind of between the.
And there is data available that actually subdivides it into subregions of time, so that you can figure out,
you can do it, yeah, because our data, so the X-ray data are event files, and event contains localization of each photon. So localization, so location, energy, and time. So you have full 4-dimensional information for each event.
Cool. Okay. Interesting.
So you can divide the whole event list, because these are tables in based on time. Let's say time chunks.
Yeah. That actually reminds me of another thing we thought about, which is that we mentioned sort of incorporating the size of the region and also the size of a confidence interval for the number of signals in that region into our objective function. But we, in principle, could actually do a multi-dimensional thing where we output regions that we interpret as having high probability of both covering the location of the signal, but also, for instance, the intensity of the signal, potentially in multiple bands. So, in principle, we could output, I wouldn't even call it a region anymore, but output sort of information about each of the signals that is sort of multi-dimensional and hopefully covers everything. And that could all be incorporated into our optimization pretty easily, because you just compute the posterior inclusion probabilities in a slightly more complicated way, and then plug it into basically the exact same set of optimizations.
Yeah.
In the generic problem that, or generic X-ray, not really generic, I guess, but the problem, the X-ray problem that Anita is describing, I'm not 100% sure what the underlying, because you need this underlying Bayesian model, right? So this is like, this is a wrapper on top of that that helps you, decide where your sources are essentially, but you still need an underlying model. So what exactly, it's the posterior inclusion probability. What is it exactly that you need to compute?
So it is, I think the easiest place to see it is here, I think, yeah. So it's the expectation, of IG given the data. So IG is just the indicator function that G contains a signal. And more generally, if we think about more sort of general power functions that incorporate other aspects, it's the indicator function that sort of G is a true discovery, right? So if we have G and J, we also need J to contain the true number of signals, right? If we had also a region for the intensity, we would need the intensity to actually fall in that. And again, that indicator function is super easy to compute if you have samples from your posterior, right? Because you can just evaluate that indicator function on each of the samples and then average it over the many samples you have. That gives you your PIP estimate.
Sure. So what you need is a model that has some sort of latent variable that says, is there a source here or here, right? Because the GRs aren't in my model, right? So you put your GRs on top of the image. So I'm not sure.
But I think almost any model would have that if it's a model for the sources, right? Like somehow any model that models the sources must have a location for those sources as part of the output, right?
Yeah, but so it might be, okay, well, you could have a model where that's fixed, for example.
But then it's not, I guess it's not a model for the locations of the sources, at least.
No, yeah.
There would be nothing to learn there about the locations.
Or you could have a model that's just telling you about how the intensity varies over the image, but without really specifying what is what's the source and what's not, essentially, right?
That's true. Although I would imagine many models doing that would have a latent variable for where the sources are, since they would come from the point spread function that would sort of tell you where there's higher or lower intensity. If there are point sources in the data, it seems like the easiest way to model that would be to also model where the sources are and then add a point spread function to that. That's certainly what StarNet did, but I guess you don't have to.
Yeah, so they might, okay, so I'm thinking of models that aren't necessary. So maybe we're just thinking about point sources. So
Yes.
you have extended sources that vary in intensity, and then you need to have some kind of non-parametric thing, and then you might just forget about, what is the source, right? Like,
That's right.
if the source itself is varying, right, over the image.
Yeah, I think it's less clear how we would apply this, and even really what the objective is when you have more spread out sources.
Standard sources, yeah.
And
So
I think
Vinay has this, maybe Anita, more about, there's this source detect. Is that what Vinay, that stuff he did in the 1990s?
Wave
Is that what it's
detect.
called?
Wave
Say it again,
detect.
wave detect, that's right, wave
Wavelet.
detect.
So this is the wavelets, and there are sliding box where you have the cells which are, the size of PSF, and you slide around the image. So for the source and for the background cells. So there is cell detect and there is wave detect, where the cell is calculated as a wavelet, and because of the wavelet you can have the background incorporated into the wavelet. So it's kind of, yeah.
The question would be, if with those methods, if there's I guess there is an estimate of source locations that come up. I'm not sure it's really probabilistic, like Bayesian.
I think he pointed us to this when we chatted with him.
Wavelet is not, wave detect is not Bayesian, but you have, you get the location and the sort of this size of the error ellipse. And
But you might be able to kind of interpret it in a, you know what I mean, like a post hoc Bayesian.
Yeah,
way.
so that's what we do in the pipelines for the catalog, that we basically run. Wave detect sources are input, and then we run post-processing with the fit.
If I remember,
fit, right?
If I remember what Vinay told us, it had some measure of uncertainty, but it didn't really have any statistical properties. It was just sort of a heuristic measure of uncertainty that there was no. I don't think he had said that there wasn't really any statistical principle behind the uncertainty quantification they had, to the extent that there was anything. It was mostly about the point estimates of where the sources were.
Yeah. Also,
So would that be sufficient for you? I mean, because you need, well, I guess you need a probability, right? So if there was some sort of iteration, well, that would be fine. But of course, probably there isn't. He probably ends up with just a point estimate.
Right. Yeah, I don't think it would be sufficient for us.
Yeah.
Yeah, post-processing, which catalog does, gives you the probability sort of, MCMC distribution just around the maximum likelihood point. So it's kind of the bootstrap type.
Yeah.
Well, actually, what,
yeah. Sorry?
what does do this is David Jones's stuff.
Oh, yeah.
It's I co-authored, but now I can't remember what it's called.
eBasc.
eBasc, yeah, or Basques, yeah.
Basc.
Because then you do
eBasc once, yeah.
eBasc, because there's a what do you call it, reversible jump, where you add in, you're fitting the number and the location of the sources, but there's not a clear detection, like controlling the type 1 error sort of thing in there. It's just you have a Bayesian estimate from the posterior distribution of the number of sources. So that might be a nice thing. You could try to paste this on top of that.
Yeah.
Did we talk about that, Asher? Is that
Can you remind me of the name? I just missed it.
Basque. So it's David. The authors are Jones, Van Dyke, and Kashup. I can send you the link.
Yeah.
Basque is the acronym. Bayesian source.
I don't think we talked about that. That sounds great.
Yeah, we'd love to see that. Thanks.
I could imagine a world in which you basically combine the wave detect squares with some, sparse patient prior, and like sort of turn that into a posterior probability for each square. In which case, then that would be that would be exactly the input that blip takes. Now, I think Vinay mentioned there were some challenges with wave detect they ran into. Like, I forget how much information about the point spread function it incorporates.
It does, yeah.
But yeah, again, the sort of the recipe with blip is like you take the best Bayesian model you can fit, whatever either is computationally practical or whatever you really believe, and usually you can turn that into an input for blip. So hopefully, if you came up with a Bayesian version of wave detect, it would do that.
It's an interesting point. Yeah. Convert to Bayesian wave detect. So I had a slightly different question. So if you have the hot pixels on the detector, which you don't know that they are there, and you have to sort of include the detection of, this is your false source, and I'm thinking about optical cameras where it can happen. Is there a way to deal with it somehow by reducing the detectability of such events in your algorithm? Because those can be characterized, I think, pretty well. You're
saying there are false sources that are...
Yes, they, like you have this detectors which over time age, and you have this flickers of the pixels, which are just the detector noise, right? And you don't know exactly when this flickering happens, but they interfere with your source detection or localization of the source, because you may, in optical camera, you may point at one source and try to localize that source with huge PSF, but because of this flicker, the localization is not great. And localizing the peak of the source within this flicker.
Could we think of this as sort of part of the background then? Sort of a different type of background, but
yes, but it's not. Yeah, it's because it's the detector. It's not well described as a background, because it's a detector background, and it's hard to predict. I mean, it's not.
But even as long as it's modelable, I think it's fine in the, or in principle, at least it could be incorporated, but you're saying it's hard to model or it's hard to predict?
Hard to predict. I don't know. There is model. I mean, you have data. So, over the course of the mission, you have data, and you have the database where you can look at this model, right? And I think there is a model of the background which incorporates this flickering.
Okay. Yeah, it sounds like something you would want to incorporate just into the Bayesian model in the first place.
Yeah.
Do it.
I'll talk to people.
Yeah.
And ask them to look at your algorithm too.
Yeah, great.
For this, maybe it's something they can use. David put in chat. There is a link, right?
Yeah, Asher saw it.
Yeah. Okay.
That's the Basque paper.
Great.
Any more questions? Anybody? We just dominated the discussion, David and me. Nobody else. All right. Okay. Well, thank you very much. And
Thank you.
hopefully we'll see you in person one day when we start getting this in-person discussions.
Yeah, that'd be fun.
Okay. Thank you.
Absolutely.
Yeah.
Thanks so much.